All right, so welcome back to another video for Transport 1, and this will be homework 3. In this video, we're going to explore a situation of, let's say, something like a water tower, right? Which has a vertical pipe and water here, and it flows downwards and out towards the city, and it has some flow rate Q out here, okay? And this, with this situation, we're going to code and find a couple of ways to calculate the friction factor, then head drop given flow, and flow given head drop. And you'll see why the last one is rather complicated. Okay, and like most things in Transport 1, this starts with the concept of Bernoulli's equation. And you've seen that plenty of times now. It looks something like this, right? And then the velocity term, and the gravitational term. And this is all equal to frictional heating, right? In this case, frictional heating is not negligible. Many times in chemical engineering, it's often convenient to represent this in something called, head form, right? Again, for this situation, there will be no change in velocity, so this goes to 0. And this head form is very simple. You pretty much divide everything by g, right? So now we have P2 minus P1 over rho g plus delta z is equal to negative F frictional heating over G. Okay. And where this frictional heating is going to be represented by, and I don't have this memorized, so I've referenced here, this frictional heating is represented by 4 fanning friction factor, delta X velocity squared over 2, right? Where am I? There we are. And then where it's this is going to be negative. I made it negative and divide by g, right? And this is going to be equal to that. We can cancel out. In this case, we don't need to represent it in a term that looks like velocity, so we can go ahead and simplify that constant, right? And by the way, this delta z we can represent as h, height. Okay, and this delta x here would be length. Okay, where velocity, we don't know velocity, but we can represent it by the flow rate, right? Where the flow rate is equal to the area of the pipe times the velocity. Okay, where q is equal to the area of the pipe, we can represent it as pi r squared v. We would like to represent it in diameter because that's usually how these equations go, and this turns into pi d squared over 4 v. Isolate for v, we get v equals 4 flow rate over pi d4. Okay, so these are going to be our equations of interest, for our Python code, okay? And we'll move into it as such. Okay, now that we're all done with our derivations on the iPad, we've hopped back into Python, and I've copied down our derivations in a digital form just so it's a bit more convenient for me, okay? So we can go off and use the Churchill equation, which you can grab directly from Wikipedia, and it's going to be a function of the Reynolds number and this epsilon over d, epsilon being a surface roughness of your pipe. Okay, so that will calculate a friction factor. On Wikipedia, it actually uses the Darcy friction factor, whereas we want to use the fanning friction factor. So this F over 8 will rather become a F over 2. And we've also grabbed our derivations for head drop from the Bernoulli's equation down below. So the first task at hand is to write a function that calculates the friction factor. So let's do friction factor, RE and ED. And that's pretty simple. It's a simple matter of just copying this over. So 2 times 8 over RE, 12 plus 1 over theta 1 plus theta 2 raised to the power of 1.5 raised to the power of 1 over 2. Oh, good. Go off and define theta 1. Theta 1 is equal to negative 2.457 times log of 7 over the Reynolds number raised to the power of 0.9 plus 0.27 times epsilon over d raised to the power of 16. Hopefully I don't make any syntax errors here. Theta 2 will equal 37530 over the Reynolds number raised to the power of 16. The next task at hand is to calculate the head drop given flow. In this head drop equation down here, we notice that, well, flow is being used in the velocity term, which is on the right side, which tells me I'm going to be calculating the equation on the right side. So let's go off and, by the way, we have some parameters defined, rho, density, viscosity, and g. And you notice that the density and viscosity defined lines up with that of water, okay? We'll go off and calculate a head drop function, which will take in given flow. It's going to also need to know I believe the length of the pipe, the diameter, and the ED value. Pretty sure. And we're going to return this right hand side, sans the negative. 2 times L times V squared divided by D times G. Okay? Next, we need to define our, let's do our V first. We need to know our velocity, which is 4 times Q divided by np.pi times D squared. From velocity, you can find the Reynolds number, which is rho v d over mu. And I believe we're all good. Everything is defined. Let's test it. Head drop, given something like 10, 0.1, 10, 0.1, and like 5 e to the negative 3. Gets us something like this. Okay, I believe we can move on. Well, that number seems funny to me, but we'll keep moving on, and if I run into an error, we'll know if there's an error or not. Okay, all right. So to move on with the next part of the homework, which is going to be solving for the flow rate given head drop, we're going to need, this is going to be a nonlinear equation, which means that we'll need to use the SciPy root solver, and we've used that plenty in the past. One thing that's different this time around is that these equations are a little bit finicky. In the past, we have been able to guess something that's pretty generous in terms of error, and the solution will still converge. Whereas this time, it's not so true. The root solver has a lot of trouble converging on a solution if we don't provide it a good guess. So we need to do a little bit of handiwork and be a little intelligent about what guess we need to provide for Q, flow rate. And to start off, we're going to start off by defining, well, bringing out our equation, which relates the frictional heating to fanning friction factor, right? And I've went ahead and divided both sides by g to get things in head form. Therefore, this expression is our head drop. You'll notice that we don't have q yet, but we have velocity, and we can relate the two by the equation of continuity. For a pipe, the area in diameter is going to look like d squared over 4, pi d squared over 4. Okay, so v equals q 4 pi, nope, 4 over pi d squared. Okay, so let's go ahead and isolate for that. We can go ahead and cancel out our constants, and we get this. We'll get q is equal to head drop times g times the diameter over the friction factor. Oh, don't forget 2 down there. 2, the friction factor. And delta x will be length. And we're all good. We next should take the square root to get q, and then multiply by the geometry. So that will be pi d4, nope, squared over 4. All good. So, in essence, this expression here we'll use to generate a viable guess for our flow rate. And we'll go off and use the root solver function as we always have. So, let's hop back into Python and we'll test that out. Alright, now that we're back in Python, I've went ahead and digitized our solution for finding a good guess earlier, and we'll go off and code this out. So we want a function for Q, flow rate, with a given known head drop and the same arguments for this constants. Okay? Oh, define, there we go, that was the function. So within this function, we'll want a function to root solve. So let's define this f of x. And as a reminder, what root solver is something that will try to adjust a independent or set of independent variables so that the solution reaches 0. Okay, so our vector will be one-dimensional, and the parameter it's going to be adjusting is flow rate, q. Okay, and we want to return a vector as well. This often is worked in systems of equations, and we want to return an expression that we want to make 0. In other words, the difference between our known and the iteratively solved head drop. Let's do that, head drop for the independent variable. All good. Okay. From all that, we return the root, and we're root solving f and plugging a q guess, right? That q guess will be solved for by first defining f guess to equal 0.1 and q guess to equal this expression on our right. So let's go off and do that. np.pi times d squared over 4 times np dot square root hd times g times d over 2 times f guess times l. All good and all good. So to make sure this works, this is essentially the reverse of the head drop function, right? So we want to go off and input that for our known, right? Then 10 and 0.1 and 5e to negative 3, and we should get something close to 0.1. Q guess is not defined. What? Q guess. What do you mean Q guess is not defined? Oh, I put it inside of I put it inside the root solving function. this should go outside. That's better. Head drop up. That's because this should be lowercase. Function and float. Right here. What happened? Oh, right here. This, I believe. This is, oh. That's right. This should be known, not head drop. Head drop, it's recognizing head drop as a function. And look at that. Look at that. And let's actually extract, do this, extract the solution from the dictionary. Look at that. When given the solution to head drop, the root solver successfully converges on the expression that was plugged in here. Remember that this function is not at all aware what this function was originally fed, so the fact that it can find that 0.1 value for the flow rate based on a head drop of 25.18 means that our function works pretty well and to a rather large degree of accuracy. Okay, so this is actually going to conclude the video for homework 3, and tune in next time for another video.